Okay, so today we're going to be looking at inference about prediction. One of the most common reasons to fit a line to data is to predict the response to a particular value of the explanatory variable. The method is simple. Just substitute the value of x into the equation. So we've done this plenty of times. For example, in the review problem, if you wanted to predict the SAT score for a student with a high school GPA of 3.5, you'd take the regression equation, which was y hat equals 269.20885 x plus 276.5751. You'd plug in 3.5 for x, and you'd get 1,218.8. But then we might want to know how accurate is our prediction because we know there's variability in the world. So in order to do that, we'll calculate a confidence interval to find out. But first we have to decide what we're trying to predict. Do we want to predict the mean SAT score for everyone with a 3.5 GPA? Or do we want to predict the SAT score for one student with a 3.5 GPA? In either case, the actual prediction of 1,218.8 is the same, but the margin of error is different. We need a larger margin of error to pin down one student's result than to estimate the mean of a lot of students' results. So I want you to take a minute and think, using your knowledge of the sampling distribution of x versus the sampling distribution of x bar, explain why we need a larger margin of error for an individual student score than we need for an average score. So remember, the sampling distribution of x, if it's from a normal population, would be normal with a mean of mu and a standard deviation of sigma, while the sampling distribution of x bar would be normal with a mean of mu and a standard deviation of sigma divided by the square root of n. The sampling distribution of x bar has less variability than the population that x came from, so it's going to have a smaller margin of error. So when we go to make a confidence interval for a mean response, it's going to have the same format as all confidence intervals do. You start with your point estimate, then you do plus or minus your critical value, which is going to be t star in this case, times your standard error. So the standard error formula is s times the square root of 1 over n plus x star minus x bar quantity squared divided by the sum of the x squared minus the sum of the x's squared divided by n. So you're going to need your calculator to help you get these values. For most of them, you're going to use 1var_stats. And if you put your explanatory variable in L1, you're going to run your 1var_stats on L1. You will get out x bar, you'll get out sigma x, you'll need sigma x squared, and you'll need n. And so in the data that I gave you at the beginning of class, x bar is 2.7987, sigma x is 41.98, sigma x squared is 120.1044, and n is 15. Now the other thing we need is s, and s comes out when you run your Lin-Reg t-test on the data. And of course, as with other regression problems, our degrees of freedom are n-2. Now, if you are going to be doing a prediction interval, it's going to follow the same format. A prediction interval is what we call a confidence interval for an individual. So you start off with your point estimate, then you do plus or minus your critical value times your standard error. So this formula for the standard error for a prediction interval is very similar to the last one. The difference is right here. We're adding on increased variability for the individual, and so there's a 1 added to the expression under the radical. The assumptions for confidence intervals and prediction intervals are the same as for inference on linear regression. We need to make sure we have a simple random sample, that the true relationship is linear, that the standard deviation of the response about the true line is the same everywhere, and that the response varies normally about the true regression line. So we already did that for this problem when we did the review. So we're going to just go ahead and say see above when we get to that point. So let's go ahead and start with a 95% confidence interval for the mean score of students with a 3.5 GPA. So this time the parameter that we're defining is mu hat, which is the mean score of students with a 3.5 GPA. So the formula we want to use for that, for this confidence interval, is y hat plus or minus t star times the standard error for mu hat. So the assumptions, we would normally go through the whole check, but we've already done that. So I'm just going to say see above. The pieces we need y hat, which is 1,218.8. We need our degrees of freedom, which is 13. We need the t star, which if you look it up on the t-table would be 2.160. And then when you ran your Linreg t-test, you knew that S was 160.080 when you did the review problem at the beginning of class. So now finding that standard error for the mean, that would be S times the square root of 1 over n plus x star minus x bar squared over the sum of the x squareds minus the sum of the x's squared divided by n. So plugging in, we have 160.080 times the square root of 1 over 15 plus 3.5 minus 2.7987 squared divided by 120.1044 minus 41.98 squared over 15. So take a minute, punch that in on your calculator, and you should end up with 80.7802. All right, now that we have the standard error, we can go ahead and plug into our formula. So we have 1,218.8 plus or minus the t star value is 2.160 times the standard error is 80.7802. So when you evaluate that confidence interval, we get 1,044.31 to 1,393.29. So then to interpret this, we would say that the mean SAT score of students with a 3.5 GPA is between 1,044.3 and 1,393.3 with 95% confidence. Now a prediction interval would be very similar. This time, the parameter we're defining is a y hat, and we'll call it the prediction for an individual student with a 3.5 GPA. So assumptions, I'm going to say see above again. Now the only thing that's going to be different is in the calculation of our standard error. So remember, the difference between the two formulas is that this one has a 1 added under the radical. So if you second enter, you should, or go up and press enter, you should be able to edit your equation and just add that 1 under the radical. And when you finish evaluating, you should get 179.3071. So you can see that it's more than twice as big as for the mean. So plugging in for our 95% prediction interval, the equation is y hat plus or minus t star times the standard error for an individual prediction. So that's going to be 1,218.8 plus or minus. The t star is the same because our degrees of freedom are the same, and it's still a 95% level. So 2.160 times our standard error, which is 179.3071. So the interval ends up being 831.5 to 1,606.1. which I think is at one point impossible on the SAT. So the interpretation of this level would be an individual student with a 3.5 GPA will score between 831.5 and 1606, although you might want to comment that it's probably only 1600 since that's the highest score possible, with 95% confidence. Okay. And as we've said a couple times, this prediction interval ends up being wider than the confidence interval for a mean score, because it's much harder to pinpoint an individual because there's more variability than it is in the mean, which has less variability.